Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss the superalloys in case of cobalt base and mostly iron nickel base. In the earlier classes, we have specifically discussed the nickel based superalloys and its application, and today we will try to look at what are the benefit or disadvantages of these other superalloys, means cobalt based or iron based superalloys compared with the nickel one. So, there are a few facts in case of a cobalt based superalloys, because one can always raise a question that cobalt has a hexagonal closed pack structure. So, for designing a superalloys, mostly a matrix of FCC structure is preferred. So, in case of cobalt, actually we add chromium which stabilize the FCC matrix phase in case of a cobalt based superalloys. Now, if we look at the composition range, you will see the chromium range is very high. So, there are two major type, one is the wrought alloy, another one is the cast alloy. So, wrought alloy was developed earlier and the cast alloys are, let us say, more advanced alloys. Now, here also, like nickel based superalloys, we add some solid solution strengthening element like molybdenum, tungsten or let us say tantalum. So, there are these alloys shows quite a large or high amount of addition of tantalum and tungsten as well as molybdenum. However, here also nickel is added for the solid solutioning purpose, and the strengthening effect mostly generated due to the presence of carbides. So, the cast alloys are mostly strengthened by the carbides, and to form carbides we need consideration of adding carbon here. So, please have a look at the carbon concentration here 0.3, 0.5 and 0.45. So, it will easily form some carbide with the refractory metals. Okay. Now, niobium is one of the good refractory metal to form carbides and which is also preferred. However, the majority of the cobalt based alloys so far is under use, they do not have any gamma prime phase. Okay. So, definitely you expect that if there is no gamma prime phase, so precipitation hardening is not really available in this system, means cobalt based superalloys. So, strengthening one part comes from the carbides or borides, and therefore, the strength level of these cobalt based superalloys are relatively low than the nickel based superalloys. However, there are some very good advantages, because we can produce sheets out of these cobalt based superalloys because of their good weldability, and weldability is better because we need not to take care of this gamma prime phase in the matrix. So, we apply basically these alloys in case of supercharger brackets, and the major disadvantage of these alloys that there are some hot corrosion which is quite severe, and also the cobalt as a element is very expensive in comparison with the nickel base pure nickel, let us say. And therefore, a common tendency has been observed that there is some diminishing trend of this use. However, there are some specific areas where we definitely need these cobalt based superalloys. Here one of the very common cobalt based superalloys are MAR M509. In the left hand side, I show you a typical microstructure of a cobalt based superalloys. The alloy name is hase 25. Here you do not see any gamma prime phase, but what you see here, these kind of precipitates, they are all M6C type of carbides along with some A2B, or let us say some of these precipitate A2B type. If you compare the properties in terms of rupture strength for thousands hour, here this is a strength in megapascal with the temperature. So, it is for sure for other superalloy, if you compare let us say one of the very famous cobalt based superalloy, the strength level is low. However, it can have a quite wider temperature range and the fall is not so sharp as the other base superalloys. So, this is one of the benefit of let us say the cobalt based superalloys on its use. So, the typical application areas in cobalt based superalloys is relatively lower temperature and lower strength level than the nickel based blade alloys. So, like AI resist, this is also one of these superalloys cobalt based, where we produce sheets or tubing and let us say gas turbine engine combustor, or let us say the flame holders, liner, some of the ducting. In case of hase 25, the microstructure I have shown you here, GT combustor liner is often used, where the good formability is one of the property and high strength up to 816 degree is required and oxidation resistance is quite high. Okay. So, also for aggressive environment, let us say sulfidation or resistance to wear, these hase 25 is also a good alloy. Now, in case of MAR M918, this is also another important alloy where we can produce those kind of high temperature sheets and fasteners, springs and so on. So, cobalt based alloys also occupy a quite large region of application in gas turbine engine in several other component, where the stress level and temperature level is relatively lower than the disc and the blade application. Now, the third category of these superalloys, I said those are iron based or let us say nickel iron based superalloys. Okay. So, here we need both iron content is very high and nickel must be present there. So, nickel iron are the main constituents, and since nickel and iron has a FCC matrix, and so they are very tough and very ductile. So, by just looking at its property, you could easily guess that what are the purpose of using these alloys. So, we can use them in the disc alloy because the formability is required for making the disc by forging or any kind of pressing operation. However, here besides only gamma prime phase, the appearance of other gamma double prime phase has been observed. So, this is the nickel 3 niobium type precipitate hardening is observed. So, we have basically presence of gamma prime phase and or this gamma double prime phase, and we add niobium in order to enhance the precipitation of the gamma double prime phase. At the same time, the solid solution strengthening element must be added, and the cast alloy here too we need carbide in order to pin the grain boundaries. So, if you look at these nickel iron or iron based superalloys, there are two major categories depending on the application areas. One alloy which has a very high strength level and it is used for a specifically precipitation hardened alloy. So, these are some of the typical series of names of the alloys like Inconel. Okay. So, here let us say the iron content is very high and you could easily understand if in a alloy iron content become higher, then we expect a lower cost. So, this is a big advantage of this nickel iron or Inconel alloys. Now, the second types of nickel iron alloys are used for a low thermal expansion coefficient. Means I may have a component or let us say a blade which is rotating inside a casing and the gap between casing and the blade has to be reduced. Now, temperature will increase, the casing will also increase, right. So, in that case one should specifically look at a low thermal expansion coefficient, so that the gap will be minimum between a blade and a casing. So, this is a very specific purpose that a smaller clearance between a rotating wheel or a non-rotating component should be considered. So, it basically increases the overall engine efficiency, and for this specific purpose we like these nickel iron based alloys with some specific composition range that shows a low coefficient of thermal expansion, and this is also a big advantage. And since these alloys are very tough and ductile, therefore, we can have a good control over the grain size and the morphology of the microstructural constituents. So, mostly we use these alloys in wrought or other condition in the form of turbine disc, some of the forged rotors or let us say some of the compressor blade in relatively low temperature, not like the single crystal nickel based superalloys, but in some areas where we do not need such extremely high one, but we need formability which is the higher priority. So, this iron based or let us say nickel iron based superalloys are also took a large areas. So, I show you some of the composition ranges of various nickel based alloys. Here there is a series of Inconel, these are quite large, and if you have a look at the niobium concentration which is added purposely to get gamma double prime phase, the concentration is quite high, okay, in several alloys. Now, here the iron content is ranging between 66 let us say to 42%, and even in some cases it reaches to 60 and so on. So, the iron content is much higher than the nickel content. So, if you have a look at this nickel and iron content of the alloy, so please have a look, let us say Inconel 800H, which is also a very famous alloy. Here we have 45% of iron and 30% of the nickel, and then we add some of these refractory metals like molybdenum and tungsten along with some niobium, and here too we need carbon and boron in order to specifically get some carbide strengthening effect. So, by looking at the composition chart, one can easily understand the purpose of the various alloying elements and their role. So far we have discussed three major types of superalloys. As I said that one is the iron or nickel iron base, and another one is the nickel one, another one is the third one is the cobalt base. So, the advantage and disadvantage, if I summarize, so far we have discussed the iron based or let us say I would say nickel iron also, because we have a high content of nickel too. So, they have always a relatively low cost and a very good workability. Okay. So, forming operation is much higher. On the other hand, it has a relatively low environmental resistance and a higher propensity for getting these kind of TCP phases which are not desired. But since iron is a BCC element, we need the assistance or help of nickel, so that nickel goes and stabilizes the phase centered cubic phase, and therefore, we need the FCC stabilizer. The typical application areas are the turbine casing and let us say the disc, and suitable high toughness application areas are commonly dominated by the Inconel series. In case of cobalt, we have the highest incipient melting point of pure cobalt. However, here also we have to add some chromium, so that it stabilizes the FCC matrix. However, they have also very good corrosion resistance, but there is no strengthening comparable to gamma prime and gamma double prime phase, and therefore, we only need actually the carbide and borides in order to strengthen the alloy. However, here also we need a FCC stabilizer, because this is a hexagonal closed pack structure. Okay. In case of nickel superalloys, we have discussed here, this forms basically these gamma prime phases or sometimes gamma double prime phases, and there is no requirement of the FCC stabilizer, and there is always a lower propensity of the TCP phases, which is avoided by some sort of ruthenium and other element. So, this is a large application areas in case of gas turbine engine, vane, and let us say the blades, where there is no other superalloys which can compete with the nickel based superalloys. So, these are the let us say the summary of all the different superalloys so far we have discussed. And if we look at some of the average composition ranges of various alloying element that I have summarized here, where iron based, cobalt based and nickel based alloys are present, and their addition of the different alloying element, including the ruthenium and aluminum, titanium and chromium. So, the refractory metal and carbide formats are also added in some extent in all these alloy compositions, whereas iron content could be in average something like 43% in case of a iron based superalloys, and carbon and boron, they are all added to get basically the effect of carbide in most of the cases. Okay. So, in general the composition ranges has been preferred for some specific alloy addition and their stabilization of some phases. So, this is all about the superalloys. However, we further improve the properties of the superalloys by adding some coatings on it. So, if you remember in the last week we were discussing about different types of coating, and in case of these superalloy blades also we apply coating, so that the performance of the blade or let us say the failure life of the blade or time to rupture, that can be enhanced further. And there are three major types of coating that has been developed. One is the diffusion coating, another one is the overlay coating, and the third one is the thermal barrier coating. And each of the coating has their own specific purpose. How? If you have a look at the diagram, we have plotted here the relative improvement in the coating life. So, the life basically increases along this direction, and this is the temperature enhancement. Okay. So, relative temperature enhancement or increment is in that direction. So, thermal barrier coating is always better than other coating, you can see in terms of service life. However, we cannot apply thermal barrier coating alone. Why we will discuss, we will talk later on. However, the question is how this coating looks like and how they are processed. Let us say after finishing of a blade, how we put some coatings there. So, there are some specific advanced technique like pack aluminization technique, okay, by which we can produce this diffusion coating. Mostly these diffusion coating are aluminum containing alloys, where it is rich with nickel aluminum and beta phase actually mostly dominating. So, in the right hand side I show you one such coating that has been developed on a gamma gamma prime matrix. Okay. So, this is a gamma gamma prime nickel superalloys, and then we have coated with aluminide like nickel aluminide by pack aluminization process. Now, if we simply put a coating, then it does not give us a good strength in terms of bonding between the coating and the base alloy. So, there is a interdiffusion zone that is beneficial in some way after some heat treatment process. So, some alloying elements will come here and there, and they will develop basically a diffusion zone or interdiffusion zone. Therefore, it will have a better one. Now, the second type of coating are the overlay coating that we said earlier, that M, chromium, aluminum and X. So, this is basically a basic composition of this overlay coating. We basically put such coating by APS. APS means air plasma spray, or let us say physical vapor deposition technique. So, this both technique could be available for producing this overlay coating. However, here these M, chromium, aluminum and X, here M basically means it could be nickel or cobalt. Okay. So, this is also sometimes often called as a bond coat. So, these bond coats are always preferred below a thermal barrier coating. Why we will come, but here I show you one schematic where thermal barrier coating is done on the base alloy. In between there is a MCR aluminum coating. So, here MCR aluminum coating. Okay. So, in case of this X, X basically stands for yttrium or some other elements. Now, along the direction of this PVD technique, there is a growth of these grains of the thermal barrier coat, and here mostly we prefer some zirconium dioxide as a constituent for this thermal barrier coating. The morphology of the grain structure of it could be different types depending on the processing condition. So, it could be columnar type or lamellar type. However, there is a oxide film in between these two coating that forms. So, here is the substrate. A substrate basically means the alloy, let us say, which is made of gamma gamma prime phase, and then on the top of it we can give a overlay coating, and on the top of it we will go for some sort of thermal barrier coating. So, here I basically in the blue color show you the different techniques that are available for preparing this kind of coating. So, electron beam physical vapor deposition is a very common technique for producing thermal barrier coat, but one should remember that if we take a base alloy, then one after another layer to be given, and like first we will go for some overlay coating, then we will go for thermal barrier coating. Now, we can think about why thermal barrier coating has a better life. So, why do not we choose only thermal barrier coating, and why we always look at the microstructure that a thermal barrier coating is associated with another bond or overlay coating. So, the problem with thermal barrier coating, even though it increases the service life, is that the expansion coefficient is very different compared to the base substrate alloy. Okay. So, if we take a gamma prime alloy and then if we apply only thermal barrier coating. So, let us say this is a thermal barrier coating, the mismatch between the thermal conductivity and expansion coefficient is very high, and therefore, we need another overlay coating or bond coating in between, so that we will get a barrier coating. However, thermal barrier coating has the highest thickness. So, the purpose here is that the thermal stresses that basically generate during thermal cycling, and that leads to the failure of this thermal barrier coating, and therefore, it basically fall from the substrate. And to get a very good adhesion with the thermal barrier coating and the base substrate, we always prefer a bond coat, overlay coat is always preferred. And to avoid this kind of problem, as I said that some form of diffusion or overlay coating must be used. Okay. Now, the second question will come that there are so many different ceramic coating we can give on as a thermal barrier coating on the top of a superalloy. Why we preferentially choose zirconia, means zirconium dioxide? There is also a reason. Okay. Please have a look at this plot. Here I show you a temperature versus thermal conductivity plot. And if you look at different ceramic material, alumina, nickel oxide, thoria, okay, and beryllium oxide, so on, the zirconia has a very stable thermal conductivity level on a wide temperature range, and this confirm us that there will be less pollution. If thermal conductivity and is very uniform over a temperature range, it always give us a better service life. So, less pollution and less stress will be generated in between the substrate and the coat. So, there are several coating that are commonly used today, and you will see it here and a summary of them. So, like these are the manufacturer like General Electric, GE, Siemens, ABB and Mitsubishi. There are various model of their turbine engine, and they have the vane and blade and the coating. So, let us say Rene and Udimat, let us say Mar, DS, these are directionally solidified alloys, and here is also a Mar series, this is directionally solidified alloys. Here you will see that we often use or they often use the thermal barrier coat along with several other kind of overlay coating or let us say bond coating. So, this is a typical composition of let us say the electron beam physical vapor deposition of chromium aluminum yttrium type of coating. So, for all these industrial and gas turbine, we have seen the role of various nickel based alloys and their specific purpose, and also in competition with let us say cobalt based superalloys, iron based superalloys. So, these three major category of the superalloys is used. However, for very high temperature application, we prefer not only the development of processing technique like single crystal production by some sort of directionally solidification and crystal selector use, we also need to apply some coating in order to achieve a better performance of these superalloys. So, with this we complete the discussion on let us say high temperature material and superalloys, and in the next week we will start a new discussion topic. Thank you very much.